Evening, everyone. So sorry for this one appearing on your homework, but hopefully you actually have enough skills to be able to work this one out. What I'm going to do is just take you through it so that you've got at least some understanding of it and can get it all handed in for your homework. So hopefully you've had a little look at the problem already. And so you know that the first thing we need to do is to find the time that the driver takes to react. We have a speed, which is 36. We have a distance, which is 7, and we need a time. Now, the thing we have to be really careful with here is our units. This is 36 kilometers per hour. Our distance is going to be 7 meters. Well, they're already different. And probably a reaction time is going to be in the seconds. So I need to convert this 36 kilometers per hour into meters per second. So 36 kilometers per hour I could write as 3,600 meters per hour, which is 3,600 divided by 60 would give us 60 meters per minute. And 1 meter per second. These are all equivalent statements. So we've actually got a speed of 1 meter per second. In which case we could just use that speed is distance over time and rearrange for time. So speed is 1 meter per second, distance is 7 and divided by time. So I can just rearrange that and get that t is equal to 7 seconds. Okay, next thing I'm going to do is part B, which is to sketch the velocity time graph. Now hopefully you've seen these before. If you haven't, there'll be a video on my website very shortly. Time goes along the x-axis, velocity goes up. I'm going to keep my units here as meters per second and my time in seconds because it's much nicer. No idea why my pen just did that. There we go. Okay, so we are trundling along at 1 meter a second for 7 seconds while we react to the situation that's happening in front of us. And then we're going to decelerate. So we're going to start to reduce our velocity to the point where we end up at 0. It will feel sharp, obviously. You know, you put the brakes on in the car and you will jolt forward, but it's not going to be instantaneous. We will have a change in gradient. We're going to decelerate. And I want to know then, I guess, what kind of time do we stop at? Because I haven't finished my diagram here if I'm just going to leave this unlabelled. Well, it's quite useful to know that the area under a velocity time graph is the distance travelled. So this little rectangle here, and we know that this one here is 7, is the 7 meters I travelled previously. So I could work out what the time is, knowing that the distance I travel as I'm braking is 8 meters. So I've got a little triangle here, and I've got a base, which will be from 7 to whatever my final time is. So I'm just going to call that base for now. Base times my height is equal to 8, and my height is 1. So I've got 1b is equal to, a half b is equal to 8, and so b is equal to 16. In which case I finish braking at 23 seconds into the situation. Calculating the deceleration of the car once it starts braking. Well, that's the change in speed over time. So it's actually the gradient of this line. Well, now I've worked out a little bit more information, that's all right. That's a change in y. So we go from 1 meter per second to none of them over 16 seconds. So my acceleration, or rather my deceleration, because of course I'm going the opposite way, aren't I? I go from 1 to that, there we go, is my acceleration is 1/16, so my deceleration is a 16th. This is the acceleration, so the deceleration is 1/16, and my units are meters per second squared. I'm going to leave part D for you to do on your own. Try and use the same kind of ideas and structures that we've used here, and do check the answers in the back of your homework to check that you're right. And if you're not, come along to a workshop, email your teacher, ask me. All the best.